Area to the x-axis. The definite integral f of x dx between the limits a and b represents the signed area between the curve y equals f of x and the x-axis for x values between a and b. So here we see the area between the curve and the x-axis between a and b. So this area. The idea of a signed area is that the integral treats the area above the x-axis as positive and the area below the x-axis as negative. So for example, this area is above the x-axis, so it would be positive. If it was below the x-axis, it would be negative. So that's the whole idea of the signed area. Once we establish that this is correct, we can use integration to calculate the areas of regions that could only have been approximated. We can explain the connection between area and integrals in two ways. One giving the link between areas and definite integrals, and the other explaining the choice of integral notation. Method 1. Let y equals f of x be a function such that the integral of f of x dx is equal to f of x plus c. Let a of x be the area between the curve y equals f of x and the x-axis for x values between a and x, where x is greater or equal to a. So here we have our curve y equals f of x. Here we have the x-axis. Here we have the point A on the x-axis and the point x on the x-axis. So a of x is the area between the curve and the x-axis for x values between a and x, where x is greater or equal to a. The area of the strip shown opposite can then be considered to be the area under the curve from x equals a to x equals x plus h, minus the area under the curve from x equals a to x equals x, i.e. the area of the strip shown is a of x plus h minus a of x. So this is the strip that we're talking about, highlighted here in yellow. So the area of this strip can be considered to be the area under the curve from x equals a to x equals x plus h. So if we were to take into account this entire area, right up from a up to as far as x plus h, and then if we subtracted the area from a, x equals a, to x equals x, so if we subtracted this area, we would be left with the area of the strip. So let's look at that a bit closer. So if we got the area between the curve, which is y equals f of x, and the x-axis, so the area in between, but if we specifically got the area from a up as far as x plus h, so this entire area under the curve right up to this point here, and then if we subtracted the area from a up as far as x, so this area, we would be left with the area of the yellow strip. So the area of the strip is a of x plus h minus a of x. We may also consider the strip shown to be approximately rectangular. So we could say that this strip is almost a rectangle. It's approximately rectangular, with area given by base by height, or as we usually call it, length times width. So base multiplied by height, or length times width, i.e. f of x multiplied by h, so base times height. Thus, a of x plus h minus a of x is approximately equal to f of x multiplied by h being the height. And solving for f of x, so we basically divide both sides by h to get the f of x on its own. We have a of x plus h minus a of x all over h. So we can call the h the base or the height or the length or the width, but it's really this little distance here. So that's the h, that small little distance there. And as that h gets closer to 0, so as this width here, or this height or base, whatever you want to call it, as it gets smaller and smaller and smaller, and the rectangle gets thinner and thinner and thinner, the strip becomes more like a rectangle. So at the moment we can see the top, technically it's a trapezium at the moment. The top of the shape, the top of the yellow four-sided shape, the yellow quadrilateral, is actually curved or slanted. So it's not an actual rectangle at the moment. It looks quite like a rectangle. But the narrower and the narrower that this gets, the closer the shape will actually get to a rectangle. So in the limit, as h approaches 0, we can treat the strip as exactly rectangular. So we can take this to be an actual rectangle when h is approaching 0. Thus, the limit of a of x plus h minus a of x over h as h approaches 0 is equal to f of x. So this is very similar to our first principles, derivative from first principles formula that we've seen in previous videos. The only difference is that instead of an a, we usually have an f. So this can be taken to be the derivative, dA dx, so differentiating a with respect to x. So the derivative is equal to f of x. If this is equal to f of x, then dA dx is equal to f of x. And then solving for dA, we get dA equals f of x dx. And then applying the integral sign to both sides, well, applying it to the left, it'll basically just cancel out that d, so you'll just get a of x. And applying it to the right, you just put in an integral sign there. So we have a of x equals the integral of f of x dx. So a of x equals f of x plus c. Because in our previous slide we had stated that the integral of f of x dx is equal to f of x plus c. So a of x is equal to f of x plus c. As a of a is equal to 0, because the area under the curve between x equals a and x equals a is 0, so obviously if this is the point A, then the area between this point and itself is 0, because there is no space in between this point and itself. So a of a is equal to 0. The area below the f of x graph, below our curve, between a and a is 0, because there is no space between a and a, because it's just itself. We get a of a equals f of a plus c. And then rewriting, we swap the a of a for 0, because we stated that up here. So a of a is equal to 0. And then solving for c, we get c is equal to minus f of a. So if a of x equals f of x plus c, hence a of x equals f of x minus f of a. Because in the previous slide we stated that c was equal to minus f of a. So we just swap these around. So a of x is equal to f of x minus f of a. So we want a of b, so b is over here, i.e. the area under the curve between a and b. So we want the area under the curve between a and b. So if a of x equals f of x minus f of a, then a of b equals f of b minus f of a. So basically swapping the x here for b. So a of b equals f of b minus f of a. So a of b equals f of x dx between the limits a and b by the definition of the definite integral. Thus, the area between the curve shown and the x-axis for x values between a and b is the integral of f of x dx between the limits a and b. Method 2. The area between the curve and the x-axis for x values between a and b can be found by dividing the region up into very large number of vertical strips, starting at x equals a and ending at x equals b. then the area of the region can be got by summing, which means adding, the areas of the strips. So the area between the curve, here's our curve, and the x-axis, between A and B, so basically this area here, can be got by dividing the region into a very large number of vertical strips, starting at A and ending at B, and adding the areas of the strips together. The width of a typical strip is dx. So for example, let's call this grey strip in the middle. This is one strip, and the width of it we're going to call dx. And its height is f of x. So the height of one of these strips is f of x. So it's like the length and the width, or the height and the width, or the height and the base, whatever way you want to call it. Then the area of the strip is f of x dx, treating the strip as a rectangle, because in theory it is so narrow. So we do treat each of these strips as a rectangle because they are so narrow. So f of x dx comes from length times width. So the area of a rectangle is the length times the width. So if this is the length and this is the width, then the area is f of x dx. Thus, when the number of strips tends to infinity, so the more strips that you break this shape down into, we say that it tends to infinity, so the highest number of shapes that we can break it down into, the area of the region is sigma f of x dx. So sigma means to add. The integral sign came from an elongated s meaning sum, which means add. Hence, the area of the region is equal to the integral of f of x dx between the limits a and b, putting in the limits of integration. In both explanations, you should know that the height of the strip is given as f of x. So the height of the strip is given as f of x. If the curve lies below the x-axis, then f of x is negative. So if the curve was below the x-axis, then the f of x would be negative. And so the resulting integral will be negative. This is what we mean when we say that the definite integral gives the signed area between the curve and the x-axis. So above the x-axis we have a positive area, below the x-axis we have a negative area. So to summarise, the area between a curve and the x-axis is given by the definite integral, so the integral of y dx between the limits a and b is equal to the integral of f of x dx between the limits a and b. This gives the area between the curve y equals f of x and the x-axis for x values between a and b. If the area lies below the x-axis, then this integral is negative. To find the area between a curve and the x-axis, it is important to sketch a graph in the required region, in particular noting the position of the curve relative to the x-axis. To find where a curve crosses the x-axis, we let y equal 0 in the equation of the curve. Then, if the curve lies completely above the x-axis, then the integral y dx between the limits a and b is equal to the integral of f of x dx between the limits a and b is positive and gives the area. So if it's above the x-axis, it's positive. If the curve lies completely below the x-axis, then the integral of y dx between the limits a and b is equal to the integral of f of x dx between the limits a and b is negative, and we have to change its sign to get the area. So if it lies below the x-axis, we must change the sign to get the area, because it must be negative. If the curve lies partially above and partially below the x-axis, so for example, here's our curve y equals f of x, and part of it lies above the x-axis and part of it lies below the x-axis. Then we must find the areas above and below separately. Then we add these to get the total area. In practice, we get the areas between A and C, so between A and C, and between C and B, separately, and then we add them. Example, find the area of the region bounded by the curve y equals 3x squared plus 1 and the x-axis, and the lines x equals 1 and x equals 3. So there was no mention here of integration, but there was a mention of area. So you want to think integrate when area is mentioned. So to find if and where the curve crosses the x-axis, we must let y equal 0. So to find where the curve crosses the x-axis, we let y equal 0. If we were interested where the curve crossed the y-axis, we would let x equal 0. So if we let y equal 0, y is 3x squared plus 1. We have 3x squared plus 1 equals 0. So we get 3x squared equals minus 1, so x equals the square root of minus a third. As this has no real solution, the curve does not cross the x-axis. As 3x squared plus 1 is greater than 0, it's positive, for all x values elements of the real number set, the curve lies completely above the x-axis. So if we have a look at our graph, so here's the x-axis, here's the y-axis, and here is our curve, 3x squared plus 1. And we can see that our curve lies completely above the x-axis. So this is the point 1 on our x-axis, this is the point 3 on our x-axis. So we're interested in the area between the curve and the x-axis between the points 1 and 3. So we're interested in this grey area. So the area is equal to the integral of y dx between the limits 1 and 3, which is equal to the integral of 3x squared plus 1 dx between the limits 1 and 3. So we just swap the y for 3x squared plus 1. So remember, for us for the area, we want to think integrate. So to integrate 3x squared, we add on 1 to the power. So we get 3x squared plus 1, and that's divided by the power plus 1, so divided by 2 plus 1, which gives us 3x cubed over 3, which just gives us x cubed. And the integral of 1 will always just give us x, and the reason for that is 1 is really x to the power 0 plus 1, so we write 0 plus 1 as our denominator, and x to the power 1 over 1 is just x to the power 1, which is just x. But it's good to just learn off the integral of 1 is x. So now we have integrated, we have to apply our limits. So we take the upper limit, which is 3, and we swap each of our x's for 3. And then we subtract, and then we take the lower limit, which is 1, and we swap each of our x's for 1. And we end up with 28. So the area, the grey area between the curve and the x-axis between 1 and 3 is 28. Let f of x equals x cubed minus 4x squared minus x plus 4. Part 1. Show that f of 1 equals 0 and find the three roots of the equation f of x equals 0. So if f of x equals x cubed minus 4x squared minus x plus 4, then f of 1 equals 1 minus 4 minus 1 plus 4, which equals 0. So we've shown that f of 1 is equal to 0. So if f of 1 is equal to 0, then x minus 1 is a factor of f of x. So we set up our bus stop method. So we have our bus stop, and we put our function underneath the bus stop. So x cubed minus 4x squared minus x plus 4 goes under the bus stop. And we put x minus 1 in front of the bus stop. And then we divide in. So we start with the x cubed and the x. So we take the highest power of x outside the bracket. So we have x cubed divided by x, and x cubed divided by x is x squared. And we write x squared on top here. And then we multiply the x squared by the factor, which is x minus 1. So x squared times x minus 1 is x cubed minus x squared. And we write this under here. The x cubes will cancel. Minus 4x squared minus 1x squared. When we change that minus to a plus, so we get minus 4 plus 1, which is minus 3x squared. And then we bring down the minus x, and then we start again. So we have minus 3x squared divided by x, gives us minus 3x, which we write up here. And minus 3x we multiply by the factor x minus 1, and minus 3x times x minus 1 is at 3x squared plus 3x. So we write that down here. So then we go again, these will cancel. We change this to a minus, so minus 1x minus 3x is minus 4x, and we bring down the plus 4. And then we go again. So minus 4x divided by x gives us minus 4, and then we multiply in the factor. And minus 4 by x minus 1 is minus 4x plus 1. Let me write that down. They both cancel, we're left with 0. So our other factor is x cubed minus 3x minus 4. Thus, if f of x is equal to 0, and f of x can be rewritten as x minus 1 multiplied by x squared minus 3x minus 4. If we factorize the x squared minus 3x minus 4, we get x plus 1 times x minus 4. So if x minus 1 is a factor, then x equals 1 is a root. If x plus 1 is a factor, then x minus equals minus 1 is a root. And if x minus 4 is a factor, then x equals positive 4 is a third root. So these are the three roots of the equation f of x equals 0. And we can see the curve drawn in on our x and y axis. And we can see there's one of the roots, minus 1. There's the other root and the third root. So the roots are the places where the graph crosses the x-axis. Part 2. Find the area of the region bounded by the curve y equals f of x and the x-axis. So the curve y equals f of x crosses the x-axis at minus 1, 1 and 4. These are the roots. So minus 1, 1 and 4. Let A1 be the area above the x-axis. So we're going to call this area above the x-axis A1, highlighted in yellow. And A2 be the area below the x-axis. So this area, this grey area here is A2. So we need to find both areas and add them together. So we're going to start off with A1. So we want to find the integral of y dx between the limits 1 and minus 1. So between minus 1 and 1. So we want the integral of x cubed minus 4x squared minus x plus 4 dx between the limits 1 and minus 1. So integrating x cubed, we get a quarter x to the power 4. Integrating minus 4x squared, we get minus 4 over 3x cubed. Integrating minus x, we get minus a half x squared. And integrating 4, we get 4x. So now that we've integrated, we substitute our limits in, starting with the upper limit, which is 1. So swapping each of those x values for 1. Then we have a minus, and then we do the same with the lower limit, which is minus 1. So swapping each of these x values for minus 1. And we end up getting A1 equals 16 over 3. So the area is 16 over 3 of A1. So now we're going to find the area of A2. So we do the same thing, just this time with different limits. So we have already integrated. So this is our integration, which is the exact same as the previous slide because the function is the same. So this time we use the upper limit 4. So swapping each of the x values for 4. We have a minus, and then we use the lower limit 1. So swapping each of these x values for 1, and we get minus 63 over 4. So we have to change the sign because it's below the x-axis, and we get A2 equals 63 over 4, so positive 63 over 4. Then the required area is A1 plus A2, which gives us 253 over 12.